This talk is about some strange behavior in the spectral stability of solutions to Euler's equation with the free boundary problem in the presence of linear shear. That's my disclaimer. Everything I'm going to talk about in this talk here is about infinite depth, but that's not important. This problem persists in finite depth. And just a little point of honor here at the end, at the beginning. I really want to say thank you to everyone who's provided input on this problem. The reason I chose to talk about this and not other topics here is because my time in 2022 talking with everyone about this, it was a wonderful experience. And so I thought it was appropriate to talk about this problem here. So thank you for all of you who spent time helping me kind of work through some of the ideas on this. Okay. We're going to start with pretty pictures and a story. So what am I going to be considering in this talk? I'm looking at water waves, mostly one-dimensional waves. So you can imagine surface water waves that are moving predominantly in one direction. I'm going to be looking at periodic waves. So you can see this periodic structure here. And, these are pretty pictures to look at. So let's enjoy them for a second. And from here, what I'm going to be doing is looking at what are the stability of these types of solutions in the presence of a shear current. Now, why do we consider stability, or why am I considering stability? One, I'm going to be working with Euler's equation for the free surface problem. These equations are complicated, and so stability is one of the few ways we can get at understanding broad classes of solutions to these equations. It also gives us a mechanism for comparing with approximate models. So a lot of times we prefer to work with approximate models rather than the full equations. And if we can preserve as much structure as possible, such as conservation laws or the same sort of stability signatures, that gives us a good way to know whether or not we're in the right regime and if our approximate model is actually capturing the behavior we want it to. And of course, if we find these instabilities, we can exploit them and hopefully find other interesting types of solutions as bifurcations off of these instabilities. So studying the stability gives us a lot of information. Why consider constant vorticity as opposed to full vorticity? Well, one, full vorticity is hard. We have to start somewhere. So think of it as a baby step or a first step. The simple answer is really we're just adding more fixed physics. The real answer, for me at least personally, is what we see on the next slide. And so some of you may be very familiar with this. Some of you may not. Someone showed me this paper by Paraubased and De Silva back in 2011, and I was kind of intrigued by the results you see numerically when you consider these waves in the presence of a strong linear shear. So here's the story I want to try and tell. Here are waves on a beach. You have sort of a backwash coming here. You have these sort of round bulbous waves persisting. Okay, so maybe you've seen this. If you go and stare at the backwash at a shoreline long enough, you'll see this. We see it in the wild. And in fact, they look pretty robust. So I'm thinking about that as a signature of stability in some sense. That is, they seem to persist for a long time. And maybe if they are unstable, the instability should be small and on such a long time scale that I'm not going to see it while just standing here. So keep this in the back of your mind. We see them in the wild, they seem to persist. Shouldn't that mean there's stability involved? Well, in this paper by De Silva and Paraubased, they then go on to look at numerical solutions, and other people have looked at numerical periodic traveling wave solutions to the equation in this regime. And here's a family of increasing amplitude solutions. You can see that when you have constant vorticity or a linear shear, you get a little bit different behavior where you can have these overhanging waves or these more round and bulbous waves that look very similar to what you see here. Of course, as you continue to look at higher and higher amplitude waves, you can see more peak solutions. And in fact, there's more exotic solutions than what are shown here. But you can see that this sort of solution is captured, at least visually to some extent, by the solutions to the water wave problem. So here are the equations I'm looking at. Again, predominantly one-dimensional free surface. So imagine you have traveling waves moving in one direction. We have a background of linear shear. And we're just going to consider within the bulk conservation of mass, conservation of momentum, And then we're going to enforce that the vorticity is constant throughout. Now, if you start with a constant vorticity, at least the equations of motion say that that vorticity should remain constant for all time. We're going to impose boundary conditions, and this is the big part of the story I want to tell, which is we're going to say that we're periodic in X. At the bottom, we have a no flux condition, or just that the kinematic boundary condition at the bottom says no water is going to the bottom. And at the free surface, the velocity in the normal direction is going to basically prescribe how the surface evolves. The big thing here is the boundary condition on the pressure at the interface. I'm assuming there's no fluid above, so we have a vacuum above, and I'm going to prescribe either that the pressure is 0 on the free surface or atmospheric pressure, or in the case of surface tension, we have the 0 atmospheric, and then of course this force induced or this pressure induced by the temperature and surface tension. So this is the boundary condition I'm going to focus on. That we're prescribing a value for the pressure on the free surface. If you solve those equations and look for traveling wave solutions, depending on the strength of the shear, you can of course generate these waves that look very much like irrotational waves. In the case of favorable vorticity, let me take favorable back, negative vorticity. And what I'm plotting here is the free surface, so the traveling wave solution in black, and underneath I am plotting the streamlines at the top and the pressure contours in the bottom. And Henrik, I totally stole your visualization for that. So it's beautiful in that paper. So really like how you showed this. All right, but what happens if I switch on to strong vorticity? Now I'm including the effects of gravity here. And when I have strong vorticity or strong positive vorticity, I get those more bulbous-like waves like we saw before. I get stagnation points inside the fluid domain. But this is a real thing. This is why I'm interested. And this is what was in that Paraubased Silva paper. I get regions of lower than atmospheric pressure inside the fluid. So in this bottom picture, you're seeing pressure equals 0. There's no surface tension here. You see pressure equals 0 here, but you also see it here. And inside, this is lower than atmospheric pressure. And then, of course, we have the normal increasing pressure underneath the wave. So now I'll go back to the question about we saw those in the wild. If I have a region that's lower than atmospheric pressure inside the domain, that doesn't seem very stable. Seems like the fluid might want to rip itself apart. And so why is it that in this regime where I'm seeing that backwash on the shore and it seems stable, am I getting something that mathematically or at least physically doesn't seem correct from the equation of motion? Okay. Now, if you read the paper by Paraubased and Silva, they talk about the fact that the low pressure beneath the upper half of the wave means that the normal pressure gradient at the surface is opposite the usual direction. And this is a violation of the Taylor sign condition. So if you look at the velocity of the normal at the surface, you get a sign switch where it increases in some areas, it decreases in others. This, of course, is connected to well-posedness of the equations. And then, of course, this seems to be a signature of Rayleigh-Taylor type instability. And so another question we might ask is, well, one, are we losing well-posedness in some way? And two, well, maybe it's just for certain wavelengths that we have issues. What are those wavelengths and how does surface tension impact this? Right. So that's the story. How do we kind of, make sense of both of these at the same time? Spoiler, I'm not going to have an answer other than some interesting ways we can look at it. What I'm going to do is go through the equations of motion a little bit more detail. We're going to look at the spectral stability results, and then I'll make some commentary or some comments on the role of gravity, which was not something that we looked at initially, but thanks to conversations back in 2022, became a very interesting part of this conversation. And then we'll look at what happens in multi-layer fluids. All right. So going back to the equations of motion, I want to look for traveling wave solutions to this system of equations. So they should be periodic, not what I've drawn up here. But imagine that's a periodic traveling wave. I want to start by finding numerically those periodic traveling waves to the free surface. And then I want to look at this spectral stability, and I want to do that numerically. I'm going to, instead of working with equations that require me to solve bulk variables, I'm going to work with a formulation due to Alouette's Laplace-Samani, which basically takes you from the having to do with both variables to then just dealing with the variables on the boundary through domain. So these equations become these, where instead of having to solve this inside this unknown domain, I now solve for eta, which is my free surface, and this capital U, which is my tangential velocity along the free surface. So I just am working with the trace of the velocity or the tangential velocity on the free surface. Yeah. Now, usually there's a Dirichlet and Neumann map involved, but this is an implicit representation. The second equation, you can think about it as two equations, two unknowns. And this bar phi, or bar phi, is a test function. So you can think of this as sort of a weak formulation. This test function is special though. It's a harmonic test function, which is used to basically prevent me from having to deal with boundary terms, the integration by parts. I can provide more details on that if you're interested, but this is again extensions of work from others. So using this formulation, find those periodic traveling wave solutions, perturb those solutions with all bounded periodic perturbations, and then of course analyze the resulting eigenvalue problem and look for instabilities. So the traveling wave solution part. Normally I would say, here's the pictures, let's not worry about the numerics or how it's solved, but this is going to come back later. When we look for traveling wave solutions, it turns out you can condense those equations into one. And so we have two unknowns here. Now our free surface eta and this Bernoulli constant v. You could say maybe the wave speed and het instead, but I just kind of absorbed it into this Bernoulli constant, which comes from integrating the equations earlier. All right, so our unknowns are these two. So we're going to enforce two conditions in order to solve numerically and do a numerical continuation method to find those traveling wave solutions. We enforce the equation, and then we enforce a amplitude constraint. And this additional equation here allows us to find the appropriate B value corresponding to the free surface solution with the prescribed height given here. I used epsilon as the height, but it doesn't have to be small. To leading order, you can do this by hand and find what the solution should be in terms of capital omega, which is our vorticity strength, sigma, which is the surface tension coefficient, and G, which is gravity. But of course, you can do this numerically and use a Newton's method or some other solver to find these solutions numerically. So here we go. These are the solutions we saw. We can increase the amplitude. And as we increase the amplitude, that's when we start to see those pressure. Here, the fact that I can have a small amplitude solution and I'm not violating the Taylor sign condition, but as I increase the amplitude, I do violate it. So this is a signature that, hey, like this isn't something we can get at in terms of the small amplitude type expansion yet. Rather, it's something that has to happen for finite amplitude. It's not going to be easy to continue and do analytic work. Okay, so we're still here, and I'm looking at my time, and it's like, okay, we're going to fly through a lot, but I want to talk quickly about the spectral stability results now. We have the traveling wave solutions. What do we see in terms of instability? Well, everything's unstable. If you're familiar with quantum problem, that shouldn't be a surprise in terms of spectral stability. Everything turns out to be unstable, even without vorticity. What you're seeing here is a measure on the horizontal axis of my perturbation. This is the flow K parameter. I should say periodic, sorry, periodic traveling waves. You can think of this as a flow K parameter or a measure of the perturbation that we're applying. And on the vertical axis is the maximum growth rate. So this is just the real part of the eigenvalue associated with growth rate. This is, so if you see something that's unstable, this is Benjamin Fear or modulation instability that you can see in the water wave problem. I fix the amplitude. So that's known and expected. And if I decrease my vorticity, I see that the Benjamin Fear instability gets amplified. But if I increase it the other way, sorry, I see that I can actually suppress that modulation instability. So changing the vorticity does have a big impact on the modulation instability. You also get some additional instabilities that are easier to see, these high frequency instabilities. Okay. All right. Turns out that this agrees really well with NLS approximations. And so there's some papers where they've done the NLS approximations that show that indeed, once this vorticity strength reaches 2/√3, it completely is suppressed. And in fact, that's precisely what we find with our numerics. The blue code here is the numerical value of the largest growth rate corresponding to that modulation or long wave region. And then we see that that goes away completely at precisely the value defined by the NLS. Okay, but what about those pressure bubbles? Where's that pressure bubble signature coming in here? Well, all right, you get a hand-thrown figure to start. So as we increase the vorticity, which was once omega, but is now omega, so capital omega, little omega, sorry about that. As we increase the vorticity, there's that Benjamin Fear instability side, or the modulation of stability disappearing. That's the 2/√3 number. But those high frequency instabilities grow. Now, those pressure bubbles only exist for larger values of vorticity. So here, for a fixed amplitude, we may not see that lower pressure region. But as the vorticity gets stronger and stronger, that's when we could see that appear for a finite amplitude solution. In fact, if we look exactly where the Taylor sign condition is violated for the first time over here, well, I put question mark because the code just stopped converging. So then is that a sign of ill-pleasantness or lack of well-pleasantness in a certain sense? Let me show you what it looks like numerically. So here I'm plotting the growth rates. So this is a slightly different plot than before. You have the real part of the growth rate on the horizontal, the imaginary part of the growth rate on the vertical. And what I'm doing is I'm increasing the amplitude of the solution. Yes, there's some instabilities, but as we start getting larger and those pressure bubbles start to appear, these things start going off to infinity. And for the longest time, we looked at this and we just assumed that that meant our code wasn't working, something was wrong, until there was this paper that came out. Let me come here. Sorry, let me skip a little ahead. The paper by Mark Blythe and Eulerequations, where they looked at the case for zero gravity. When you look at the case for zero gravity, it turns out that you have analytic solutions. They're similar to the Crapper wave solutions, which means that any numerical error isn't going to come in from numerically solving the equations because we have exact solutions. And when they look at the spectral stability in the complex plane, they see also these things going out to infinity. So, okay, maybe that was a key for us to go back and look at this, because maybe what we had there all along was right, or it's telling us something. And indeed, if we take gravity to be small, not zero, but if we take it to be small, our numerical figures look very similar to theirs. And if you tweak the parameterizations, they look exactly the same. Okay. So this is interesting though, because our challenge with getting at the analysis here was because our solutions were bounded away from zero amplitude. But if we start now considering gravity as small, we take gravity to be zero, then that Taylor sign condition is always violated. For the sake of time, I'm just going to jump a little ahead and tell you the punchline. Still trying to make sense of the connection between the violation of this Taylor sign condition, whether or not these equations are actually correct in this regime, when everything seems to be unstable, but not just unstable with unbounded growth rates. That's a little concerning when things are going out to infinity. So if we look at zero gravity, I mentioned this in passing, but if I take gravity to be zero, the Taylor sign condition is always violated for traveling wave solutions. But it's no longer a singular perturbation if vorticity is strong enough. So why not just play the game of making gravity zero or making gravity an unknown, and rather force your equations to violate the Taylor sign condition of the rest. So going back to this bifurcation problem or numerically solving. Before, here are our equations, two unknowns, eta and the Bernoulli constant. why not just say, look, now as I turn on gravity, I want gravity to be unknown, but I want to find the value of gravity so that the Taylor sign condition is violated exactly at the crest. In other words, the bubble hasn't gone into the fluid, it's just kind of kissed the fluid. This is the first time that's sort of appearing. And you can do this, at least at first order by hand. I used Mathematica, got up to 8th order in epsilon, and you can get an expression. And what you end up with is gravity equals something that's a function of the amplitude, the vorticity, and surface tension. And so you can plot a, what will we say, a contour plot showing how that is impacted. And you can look at that relative to our numerics. So I'm going to wrap up with this to kind of explain a little bit of what you're seeing here. The animation is changing the strength of surface tension. Okay, so if surface tension is 0, that's the beginning of the animation. What you're seeing is for different values of gravity, you're seeing the line in the amplitude on the vertical, vorticity on the horizontal. You're seeing the line that demarks this side or to the right. The Taylor sign condition is violated, and to the left, it's not violated. So exactly on that line is the first time the Taylor sign condition is violated. And if you test the numerics on one side of that curve, it converges, and on the other side, it diverges. So, okay, what does this mean? Well, I'm going to skip my commentary here, but say that I think in the end, it comes down to the fact that we're prescribing a precise value of pressure on the free surface, because if you switch to a 2-layer fluid, where all your boundary condition now is prescribed as continuity of pressure on the interface, you no longer get this sort of blow up or unbounded growth rates. I feel like there's something easy in the problem I'm missing that should make all of this make sense, but the conclusion to myself right now is I don't like the equations in the presence of strong vorticity relative to gravity because of those unbounded growth rates. And I'm not sure exactly what that means. So any comments? I'm very, very eager to hear your feedback on it. And with that, we'll just go ahead and end. So thank you for your attention.
Thank you very much, Casey. Do we have any questions for Casey?
Okay, so I just want you to have better physical picture. If Taylor sign condition violated, you always have divergence of growth rate. Right? And if it's not violated, you still have stability, it's just not divergence.
Correct. And I should be a little bit careful because at least outside of that demarcation where we did the zero gravity, that delineation was squishy. So on one side, plus a little down the way with diverge, and on the other side,
Well, but let's have the numerics.
Yeah.
Yes.
So this, I'm an internal waves guy, so it looks a lot like trap force or presence of shear. Those have actually been measured. This just down the road from you guys, actually. University of Washington. But I guess I wonder whether the fact that you're deforming the free surface, you're deforming the part where you have the largest spectral background. I guess that would be my hypothesis. We do this too, like we do on Friday, that long equation. But we sort of get away with it because it's okay to pull in stuff from outside your domain because everything is very channeled. It's wrong and turning, but you've got this very large density difference.
and that's actually something I'm working at right now. It's like what happens in that limit as you do start from the 2-layer and let that top go to 0. It didn't work out yet. But no, exactly. I think that's pretty much it. It's the difference between describing that pressure condition versus the continuity. Yes, and I'm very eager to hear more about what you're saying. Yeah.
Yes, ma'am.
And when you do the stability analysis, do you do it only for the eta or do you do it for the original equation that you showed with the U and the
For both.
both?
Yeah.
Okay.
I do need to have both. And that's actually an interesting question because I've looked at multiple different formulations as well, because this is one of the things I thought, well, maybe is this a consequence of working with maybe a pseudo potential or something else? And to the best of It's not that,
Okay,
yeah.
yeah, just wanted to make sure.
No, that's a very good question, and I did include it, like, yeah.
Any other question for Katie? If not, let's thank the speaker again.